Now we want to continue the discussion of entailment in the perspective of the Wumpus world problem. So we kind of apply the same kind of analysis to the Wumpus world reasoning example we discussed earlier. Consider the situation in which the agent has detected nothing in 1, 1. Let's say it has detected no percept at 1, 1. We set that axiom, there's no percept, and a breeze in 2, 1. So basically at the end of step 2, there's a breeze in 2, 1. This percepts combined with the agent's knowledge of the rules of the Wumpus world constitute the knowledge base, which is given here. This is the knowledge base. Okay? Here, this is the knowledge base. Two different figures, A and B. So the percepts are no problem, no percept in 1, 1, and a breeze in 2, 1. Okay? So the breeze in 2, 1. So now the agent need to decide what is the next feasible stage to go or next feasible step to go. And we are trying to see, we already discussed that the agent is interested, among other things. So to know whether the adjacent square like 1, 2, 2, 2, and 3, 1 contains any pits. 1, 2, 2, 2, and 3, 1 are this, this, and this. Each of these 3 squares might or might not contain a pit. So for the purpose of this particular example, there are 2 to the power 3 equal to 8 possible models. We have already discussed this. 8 possible models, right? A, B, C, and we said that 0, 0, 0. We can see that like 0, 0, 0 is this one where no pit in any of them. 0, 0, 1 is where C has a pit. Let's say this is 0, 0, 1. 0, 1, 0 is this one. 0, 1, 0. The second one has a pit. 0, 1, 1 is this one, where the second and third one has a pit. 1, 0, 0 is this one, where the first one only has a pit. 1, 0, 1 is this one. 1, 0, 1, 1, 0 is this one. And 1, 1, 1 is this one. So there are total 8 possible models, and the knowledge base can be thought of as a set of sentences or as a single sentence that asserts all the individual sentences. The knowledge base is false in models that contradict with what the agent knows. So remember, as of now, as we have already said here, agent knows up to here, these 2 points. Like no percept in 1, 1 and breeze in 2, 1. Only these 2 at this stage. Unless it goes to the next stages, it does not know the other knowledges. So the knowledge base has to agree with the current percept or the current knowledge of the agent, and that's why knowledge base is only satisfied in these 3 models, not in the other models. So knowledge base is false in the other models, in which 1, 2 contains a pit. Because there is no breeze in 1, 1, right? 1, 2 contains a pit because there is no breeze in 1, 1. You see 1, 2 contains a pit in this, the first one. So this one, this one, this one, and this one. So it does not match with what agent knows, that there is no breeze in this place, so there cannot be a pit in others. So these are actually knowledge base is false in these 4 places. Now there are in fact just 3 models in which the knowledge base is true, and these are shown using this solid line, right? So now let us consider 2 possible conclusions. Okay, the first one is this alpha 1, that there are no pit in 1, 2 and there is no pit in 2, 2. These are two sentences we are trying to validate or verify, 2 possible conclusions. We have surrounded the models of alpha 1 and alpha 2 with dotted lines. So alpha 1 is this model now, this world, and alpha 2 is this dotted line, okay, for the second case for verifying this conclusion. In every model in which knowledge base is true, alpha 1 is also true. Do you see that? Alpha 1 is what? There is no pit in 1, 2. You see, in this model, there is no pit in 1, 2, no pit in 1, 2, no pit in 1, 2. So alpha 1's model also varies. That means whatever is in the knowledge base, if the knowledge base is true, then alpha 1 also true. So alpha 1 can be derived from the knowledge base. So we say that KB entails alpha 1. Okay. Because in every model in which KB is true, alpha 1 is also true. So that means KB entails alpha 1 and there is no pit in 1, 2. Also we can see in some models in which KB is true, alpha 2 is false. See, alpha 2, let's use a different color. So alpha 2 is true in this model of the knowledge base, but not in this and this model. So wherever the knowledge base is true, alpha 2 is true, we cannot deduce that conclusion. That means knowledge base does not entail alpha 2. Okay. So based on the current status of the knowledge, we cannot say alpha 2 is a true model. So the agent cannot conclude that there is no pit in 2, 2. Also, it cannot conclude that there is a pit in 2, 2. So this example does not only illustrate entailment, but also shows how the definition of entailment can be applied to derive conclusions. That is, to carry out logical inference. The inference algorithm is called a model checking. Okay, this is the inference algorithm. So this is called a model checking. So this procedure through which we have made the inference whether alpha 1 entails or alpha 2 does not entail, this procedure is called model checking. So among all the possible models of the world, we are checking if any sentence belongs to that model or validates to that model. So this is important, right? So now you can see that so this is basically, it enumerates all possible models to check if alpha is true in all the models in which KB is true. That is that MKB should include M alpha. That means we are checking, model in which KB is true also, kind of signifies or derives that models in which alpha is true. So to understand the entailment and inference, it might help to think of the set of all consequences of KB as a haystack and of alpha as a needle. So all possible consequences of the knowledge base is like a haystack, and alpha is a needle, and we are trying to find a needle in the haystack. So entailment is like a needle being in the haystack, and inference is like finding it. So this is like a needle, and this is a haystack. This entire knowledge base is a haystack. Okay, so we are trying to find if this needle is in this haystack, and this is the inference algorithm which helps us to find that. Okay, so we write it in a particular way. The distinction is embodied in some formal notation. If an inference algorithm I can derive alpha from KB, we write that KB derives alpha through the inference algorithm I. So you can say that alpha is derived from KB by I, where I is the inference algorithm, or I derives alpha from KB. Okay, so an inference algorithm that derives only entail sentences is called sound or truth preserving. Soundness is a highly desirable property. Okay, so what is soundness? Soundness is that everything derived is actually entailed. No false conclusion. Soundness is very important. Model checking is sound because it only confirms truths that hold in all models. Another thing is called completeness. The method can derive all sentences that are entailed. Okay, that's called completeness. In simple domain, we can check every model like a finite haystack, but in larger or infinite domain, completeness becomes harder to achieve. Completeness is what? The method that can derive all sentences or make an inference of all possible sentences that are entailed. And soundness is what? Everything derived is actually entailed. So no false conclusion. Okay? Thank you.